Welcome to Ingest, the podcast designed for primary care clinicians and brought to you by the Primary Care Society for Gastroenterology. My name is Charlie Andrews, a GP with an extended role in gastroenterology based near Bath. I'm joined today by James Kinross, a colorectal surgeon and the author of a widely available book called Dark Matter. We're going to be discussing the microbiome. So we're going to go on a journey into understanding some of the basics of the microbiome and the relationship it has to our health and well-being. Ingest is an educational podcast and is designed to provide you interesting and educational conversations with specialists in various areas of gastroenterology. The opinions expressed are those of the speakers, and this should not replace your clinical judgment or use of national or local guidelines. So James, welcome to the podcast. It's great to have you here.
Thank you for having me. The honour is absolutely all mine.
Do you want to start off, James, by just introducing yourself to our audience today so that they know who you are?
So my name is James Kinross. My official title is that I'm a reader in surgery, which I think in new money makes me an assistant professor. And I'm a colorectal surgeon by trade, and I work at Imperial College in London. But I did a PhD on the microbiome a very, very long time ago, and my research group looks at how the microbiome causes disease, such as cancer, and we're interested in trying to engineer it to prevent disease and to treat diseases like cancer too.
I'm really interested in the microbiome, and it's a really important and emerging area of interest within gastroenterology, and I'm sure that primary care clinicians are going to be wanting to understand about what the microbiome is. And one area that I thought we could look at, James, would be also looking at an area that you mentioned that you're interested in, which is kind of that early microbiome development and how that can impact on health later on in life. I came across your fantastic book, which I would recommend people have a look at. It's called Dark Matter, and it's really interesting, and it provides a really good overview of the microbiome. Firstly, James, what brought you to write that book?
Well, it's an interesting question. It was a sort of a catharsis in many ways. I sort of felt like I had this weight of knowledge that I just had to get out of my head, and I felt for the first time that I think I had something to say. Microbiome science in its kind of modern iteration has only really been around since 2005, and I felt that it had matured enough such that we could say things around causation that were now meaningful, because I think a lot of the early work was based on association, which is obviously different. And I felt that there was a breadth and body of work across microbiome sciences that felt a bit overwhelming, but I felt that it could be brought together into something that was more manageable. So that book is really an attempt to try and bring those different silos of work together to make a core argument. And the core argument, and the thing that I sort of increasingly believe, is that we're basically experiencing an internal climate crisis. When you start to look at human biology as an interconnected collection of complex biodiverse ecosystems, you can see that it's being affected in the same way our external climate is. And of course, they're intimately and profoundly linked. And I think that's why we are seeing this rising pandemic of non-communicable diseases, which I'm sure we're going to get into the weeds of. So that was my basic motivation.
I thought it was really interesting, which is why I was really keen to have you here on the podcast, James. So should we pull it back and just think about what the microbiome is? So could you start by perhaps explaining what exactly the gut microbiome is and why primary care clinicians should be paying attention to this area of research?
In its sort of driest definition, a microbiome is a collection of all microscopic living things and all of the stuff they need to sustain themselves within a defined niche. So the skin has a microbiome, the gut has a microbiome, the lung has a microbiome, the urogenital tract has a microbiome. And a microbiome, I suppose, has two other really well-defined features that I think are really, really important. The first is that it must have a defined symbiotic relationship with the host. So many of our organs are occupied by bacteria or microscopic life forms, some living, some not, in a transitory way. They come and they go. Like even the brain might have bacteria or microbes within it. Generally, that causes disease or harm, but it's it doesn't have a microbiome because it doesn't. Well, maybe we'll get onto that actually, but for now it doesn't. And that symbiosis, and this is the key thing really, It has an evolutionary basis. The microbes within us, and honestly, they are not there by accident. They just haven't just fallen into us. They were there before we got onto the planet as a species, and they'll be here after we've gone. And all of our organ systems have evolved, have co-evolved with them in what we would call in evolutionary biology a phylosymbiotic relationship. So bugs influence how our organs develop, and our organs develop influence how bugs develop, and they do that in partnership. The second really important thing you need to know about microbiome is that it's not constant. It's a dynamic living ecosystem, and that means that it changes with time. So the microbiome that we're born with is not the microbiome that we die with, and a microbiome will influence our health in different ways in different organs depending on our needs and depending on where we are in our life cycle. And of course, it's hugely variable. So your microbiome is profoundly different to my microbiome. We might have similar functions of microbes that allow us to grow our organs and to sustain our health. But at a species level and a strain level, we're really, really different. So it's very, very personalized. So microbiome, again, just to summarize, it's a collection of microbes and all of the things that they need to sustain themselves within a niche. It has an evolutionary basis and it is time dependent. And therefore, you need to know about it in primary healthcare because it doesn't just influence why we get diseases, it influences how we treat diseases, and also many of our treatments of diseases influence the microbiome. And I suppose as a primary healthcare physician, what you're really interested in is the particular functions of these microbes. So these microbes do everything from metabolizing drugs and breaking down the medicines we give to providing us with essential nutrients and minerals, but also to influencing and regulating our immune system. And that's obviously important for a number of different reasons.
And how does a microbiome, how do we first develop a microbiome?
What I love about microbiome science is that it is challenging dogma, right? And sometimes very passionately and strongly held beliefs around healthcare. So I think if you go back to Barry Marshall's discovery of H. pylori, right, you see that, like, as a surgeon, we used to do really terrible, awful operations like vagotomies for duodenal ulcers and gastric ulcers that just didn't work and caused awful morbidity because we couldn't possibly believe that bacteria could cause an ulcer. Lo and behold, of course, that's not the case. And I think the microbiome does that throughout many aspects of health. And one of the most profoundly held beliefs is that we're born sterile, and as we're delivered into the world, we have first contact with microbes through the birth canal and then as we breastfeed. Now, it may be that that's not the case. So the first thing to say is that the maternal microbiome within the gut, within, the urogenital tract, within the skin, influences gestational health. So it influences the health of the gestating infant, not because it necessarily colonizes the infant, but because it produces lots of small molecules that influence organ development, right? And so a really good example of that would be short-chain fatty acids, so butyrate, propionate, acetate, these sorts of molecules. The microbiome influences how the placenta grows, right? It influences the health of the infant. And what we find is that actually by the second trimester, you can find very low abundances of strains of bugs in the infant's gut. And what you can find is that actually the T cells, memory T cells at birth all have memories of these things. Now, that's really controversial. Many people believe that these are contaminants or they're not really there, but we do see this data come through in animal experiments and other kind of repeatable experiments. And to me, it's entirely plausible that they're there. So it may be the first kind of really revolutionary thing is it might be that we're not actually born sterile. But nonetheless, when you are delivered into the world, at whichever route you come through, you get colonized quite quickly. And initially what happens is as you begin to breastfeed, you'll have a super bloom of bifidobacteria. So the sugars in breast milk will drive that bloom of bifids. And of course, breast milk has its own microbiome. It's got its own set of microbes, and it's also got its own set of antibodies that shape how the ecosystem evolves. And then you'll come into contact with the world, you'll be parented, you'll have infants, you'll have siblings, you'll have pets, and all of these things will shape your microbiome. And then ultimately you begin to eat. And when you begin to eat solids, your food diversifies and your microbiome diversifies with it. What we're interested in our group is how medicines perturb that development, so particularly antibiotics and these sorts of things, because we think if that is perturbed, that's really important because what that means is that your immune system is not effectively set up to deal with a modern world, and that therefore you are more susceptible to immune-mediated diseases.
Can you expand on that? Because we give a lot of antibiotics in primary care to children. Do we understand what the effect of that is if we're giving multiple courses of antibiotics at a young age?
So the answer is no. And I think it's something that is very poorly measured and defined and not well understood. And I believe that antibiotics have not just radically shaped the human microbiome in a very short period of time, because we've only industrialized their manufacture really since the mid 1940s, although they've been around forever. You could argue that they're natural, right? But we've misused them not just in the manufacturing of medicines for patients, it's actually their misuse in farming. And it's reshaped the planetary microbiome, right? Profoundly reshaped it. Now, if you take a dose of amoxicillin or a penicillin-based antibiotic, the impact on the gut microbiome, I say the gut because that's the thing that I study, but it'll impact on other microbiomes. Its impact will probably be quite transitory and limited. You'll see a collapse in gut ecology, but most of the time it will bounce back. But if you're taking broader spectrum antibiotics, the impact can be catastrophic and it can be very long lasting. So if you're taking a macrolide antibiotic, actually we see from studies that in some patients who just lack resilience to antibiotic therapy, you get a 10 to 40,000 fold reduction in bacteria, but what regrows back is not what was there before. And it's not just that the type of bugs that grow back are different, it's that their functions are forever changed. So those molecules that they produce change and their interaction with the immune system changes, and that can be very long lasting. So if you look at good epidemiological data sets from across the world, what you see is that recurrent antibiotic use in early life increases your risk of most immune-mediated diseases like atopy, asthma, allergy, eczema, these sorts of things. It also changes your risk of obesity, and it changes your risk of cardiovascular disease, and it changes your risk of bowel cancer, and it changes your risk of multiple non-communicable chronic diseases. And increasingly, I'm of the opinion that antibiotics are a major driver of that. And just kind of one last thing, because I appreciate I'm doing a lot of talking. If you go right back to the initial studies of antibiotics in the 1940s, after sort of being given to soldiers, the next application was in farming, because we had a food crisis, because we were coming out of the Second World War and we couldn't feed the nation. And antibiotics were given at scale to animals, not because we wanted to necessarily change their metabolism, but because we just didn't want them to die of pathogens so we could get them to market, right? And very, very quickly, we noticed animals got fatter much, much faster, right? So the earlier studies, by 1948, we were publishing studies saying if you give chickens antibiotics, they get fat, right? Well, why do they get fat? Well, they get fat because you're killing all the microbes in your gut, you're driving and promoting inflammation, and it's a dysfunctional immune system that promotes insulin resistance. That's what drives it. And so, again, I'm arguing that things like the obesity pandemic, yes, they are in part driven by our addiction to ultra-processed foods and generalized kind of westernized diet. But that's because we're feeding that to a microbiome which is incompletely and improperly assembled, and we're feeding that into a gut which is inflamed, right? So it is a combination of drug food interactions which explains that.
On the antibiotic note, James, what are your thoughts? Is there much evidence behind using probiotics when taking antibiotics?
So I think there is evidence, actually. I think probiotics in some ways are much maligned. I think a lot of physicians, primary healthcare physicians, feel quite suspicious of it because probiotics feel very overwhelming. You've got, it's mainly marketing and direct to consumer evidence, which is poor quality and not very well communicated. And actually clinicians lack access to really good quality evidence. I think that is changing. I think the University of Southampton have an initiative at the moment to try and create if you like, a formulary for probiotics so clinicians can identify specific strains that they need to solve particular problems. But yeah, there is good evidence for antibiotics, and I will regularly put my patients on probiotic or prebiotic foodstuffs whilst they're having an antibiotic. So for your listeners that don't know, a probiotic is a live bacteria that has an established health benefit. Typically, what you want to recommend to your patients is that they have a high dose probiotic, so 10 to the, at least 10 to the 5, 10 to the 9 colony forming units. And you want ideally multi-strain, so 4, 5, 6 strains if you can get it, because it's going to have a bigger effect. And the other piece of advice you have to give is they've got to take it for at least 8 to 12 weeks, because those microbes have got to engraft. They're living things. It's not a drug. Those bacteria have got to get into the gut. They've got to stay there and sustain themselves. So that means you've got to keep dosing it, because these probiotic strains are not designed to live in the gut. They're not supposed to be there. And they've got to take them sustainably. And I think the much more important piece of information is that they've got to think about their diet, because microbes need to be fed as much as you need to be fed. And actually, the much more important piece of advice if you're taking antibiotics is to think very carefully about the nutrition that you take in when you're sick. So that means really no Lucozade. Like, Lucozade is the devil. It means no sugary drinks, no sweet drinks, really abandoning ready-made foods and focusing on getting a plant-based, high-fiber diet in, because that's really what your gut needs.
Thank you, James. I think that's really helpful. There's some really practical advice in there around probiotics and use when people are on antibiotics. Could we now turn to how the microbiome interacts with the immune system, which I understand is quite an important aspect here, and think about how that impacts on our risk of non-communicable illnesses and disease?
So just to set the scene, so our immune system, like at its most basic and most fundamental level, I appreciate most of your listeners will know this, but just in case, like we can think of an innate immune system, which is an immune system. It's literally your antiviral software that you are born with at birth. It's a set of cells that will kill and ask questions later. It's just an inherent defense system. And then there's your adaptive immune system, which is learning. It's producing antibodies to specific targets. And quite often think that we think about or talk about or use language for the immune system, which is incorrect, because we think about it as a Cold War defense system. We think about it in the language that I've just described. It's there purely to protect us. But I think about it more of a sort of molecular memory. Its job is to sense the world around us and to memorize the world around us and to remind us in the future, kind of when we bump into things again. So I think it's more nuanced than that. Now, your microbiome has an important role in influencing the development and the shaping of the innate immune system in very early life. And I'll give you a good example of that. So one example would be how the microbiome shapes the microglia. So microglia are kind of like macrophages for the immune system, right? They shape how both our central and peripheral nervous system grow and how they develop. And if you give antibiotics to mice early in their development, the antibiotics will shape and influence how those different subtypes of microglia will form. So you will get a completely different distribution of those subtypes. And later in life, that will then sensitize those animals differently to how they experience pain. And by the way, that happens in a gender-specific way. So that the microglial development happens differently in men and women, or male and female mice in this case. And we think that might explain why we have these kind of different risks for chronic pain syndromes, for example, and how we experience pain. But there are lots of other examples of how it does that. So it shapes the development of these innate immune systems, but it's going to shape the development of the adaptive immune system, because first of all, we like to think about when you were at med school, you learn about the immune system in a very linear way, don't you? You learn about it lots of pathways, like impossible to remember cascades with all seemingly paradoxically numbered things that just are all soluble and not soluble. And it's very hard to follow. But of course, in practice, that's not really how the immune system works. In practice, it's a complex system that is all different bits of it are interacting the whole time, and the innate immune system influences how the adaptive system works and vice versa. But more broadly, the microbiome will shape the adaptive immune system, and it will also shape its memory of friend from foe. So it has a very big part to play in influencing, for example, how T cells develop, and lots of different types of T cells, from cytotoxic T cells to T helper cells to T regulatory cells, and all of the different T cells in between. So it has this sophisticated molecular language, which isn't just one language, it's multiple different languages that it can speak, and it will then shape that immune development throughout the duration of our life. So in very early parts of our development, obviously that's very, very important, but as you get a bit more robust and you become an adult, it becomes more nuanced and more subtle. Now, it might be that, again, a dysfunctional immune system, and I've kind of give you one example of how it might influence your risk to obesity, right? But actually, it probably changes your risk to things that are probably a little bit more intuitive, like autoimmune disease risk or atopy or allergy. And we think that's a kind of a big part of the story there. It's something in how that immune system is primed in early life. And our thinking has evolved over kind of various iterations. So there used to be something called the oral gut hypothesis, where we thought that actually it was exposure to dirt. Well, that's kind of moved on to, I think it's called the missing friends hypothesis. So you just didn't have enough of the microbes. And then Martin Blaser in New York has got the missing microbes hypothesis, that actually if you don't have enough of the right microbes at a critical moment in your life because they've been knocked out through antibiotic use, that's a problem. But actually what we're experiencing is a generational loss of these microbes, right? Because actually, a lot of these microbes are passed down through your parents and through familial lineages. The way I think about this is that if you ask most conventional doctors why we get most non-communicable diseases, they will say, well, it's because you probably have a degree of genetic susceptibility and then you have a particular environment, right? They will say it's a gene environment interaction, right? And there's nuance and subtlety and complexity in those things. But I would argue quite strongly that it's not gene environment, that it's actually gene environment microbiome interactions, is what I call GEM interactions. And those GEM interactions are super personalized and super dynamic. But what you are seeing is a generational shift in that GEM interaction over time. So as we've got to a hyper globalized society, young people today in a span of 7 or 8 generations, basically since the 1940s, they've got a very, very different gene environment microbiome interaction. Part of that is the microbiome because it's lost, but also we have to acknowledge the exposome has changed, the environment has changed. Your exposure to toxins in the environment, to urban environments, to the globalized diet you have is also changing, right? And it's that interface that drives and explains this shift in your non-communicable disease risk.
Do we have evidence to show that is the case, or are we not at that stage yet? But it does appear that that's the case.
No, it's a brilliant question, and I would hand on heart say that at the moment this is a hypothesis and a theory, but I would also say this, which is that what we have very good evidence of is of the missing microbiome. So you can look at what we call metagenomes, so collections of whole communities of genes that come from microbes. And you can do that across very long time periods because we can look at what we call coprolists, so fossilized fecal samples or dental records, from Neanderthals and way back, right? And we can see the evolution of the microbiome in modern man. And we can see that things have changed very, very dramatically. And we can see the majority of that change has happened in the very recent past, like the last 10,000 years. And then that has escalated dramatically in the last, 70 to 80 years. We can also see when we look across urbanized populations and rural communities, or urbanized populations, and in fact, hunter-gathering communities and more ancient communities that live very isolated lives. And we can see that actually when you go into urban environments, the microbiome is profoundly different, right? So you lose about 30 to 40% of the microbiome kind of population of bacteria. It's fundamentally and profoundly different. But what you also see is that their functions change. And what you can also do is measure the microbiome of the environment itself. So you can actually measure a city's microbiome, and there have been big studies that have done that. And you can measure things like antimicrobial resistance genes within that environment, right? So we know that there's this very dramatic evolution of the microbiome and a dramatic loss of the microbiome. Now, a critical thing to understand here is that it's not necessarily like the difference, I suppose, with microbes and, let's say, nice furry animals that we think about when we're talking about biodiversity loss, that are on our Instagram feeds, is that bacteria they mutate rapidly, right? And they can share genes through horizontal gene transfer, and they can mutate to adapt to environmental stress incredibly quickly, right? Worryingly and alarmingly quickly, which is why antimicrobial resistance is such a problem, right? But they can do it for lots of other things. So in this changing world that I've described, there are winners and losers, right? So we've lost microbes, but we've also gained some. So if you look at Bacteroidetes as a filer of microbes, bacteria, they've been tremendously successful. They've had this great big bloom because actually they do very nicely with a westernized diet, and they very much enjoy eating McDonald's, right? So they've done very nicely, right? So it's not quite as simple as a loss, and it's actually it's changing ecosystem with a changing set of functions. The other thing that I would say is that you can then begin to map those things onto epidemiological data sets, right? And I think one of the problems that we have in clinical practice is that we all work in silos. So I'm a cancer surgeon, and I spend a lot of my time trying to understand why we have this alarming rise in colorectal cancer rates in young people. Like, why is that happening? You cannot understand that problem if you look at cancer in isolation. What you have to understand is that obesity rates are rising globally. Autoimmune disease rates are rising globally. We've got a mental health pandemic. We've got these kind of rising rates of non-communicable disease. And there has to be some commonality in their underlying etiopathogenesis. There has to be something which brings that together. And it's not going to be, what the Daily Mail want it to be, which is just one single driver, which you can very happily explain to the British public 1 week to the next. That's not what's happening. And so to understand that, what you've got to have is you've got to have a way of thinking in systems. You've got to understand how things are interconnected at quite a sort of, what I would call a top-down level. And that's why the microbiome is helpful. A traditional microbiologist wants to understand how one bug causes one disease, and they want things a nice reductionist linear pathway, right? But that's not what microbiome science says. It says, microbiome science says, how do communities or networks of bacteria, by interacting with each other, but also with the host, influence your disease risk? And when you start to look at that level, then some of this stuff you can begin to make sense of it, I think.
So James, if I wanted to find out if I had a gut full of good bacteria, and I went and found a private company online and decided to have my gut microbiome analyzed.
Yeah.
What are your thoughts around that? Is it going to be helpful for me to know what's my balance of good to bad bacteria in my gut? What are your thoughts, James?
Okay, so my first thought is that there is no such thing as good or bad bacteria. Right, it's an unhelpful thing to anthropomorphize microbes, and it speaks of, marketing from probiotic manufacturers. There are pathogens that cause us harm, which are bad because they kill us, I suppose. In that sense, they're bad. And then there are kind of mutualists, there are commensals. And the reason I bring this up is that if you treat your microbes badly enough, it doesn't matter whether they're good. If you're listening to this, I'm putting my fingers up. If they're good, then you treat them badly enough, they'll cause you harm. So actually what you've got is a set of microbes that you need to nurture and you really need to look after. And under the right circumstances or the wrong circumstances, any microbe will cause you harm. So that's the first thing. The second thing is there's a fundamental question which you've raised, which is, should we be measuring the microbiome? 100% yes, we should absolutely be measuring the microbiome. And yes, I do it in my clinical practice. There's a nuance in the answer to in the way you asked your question there, which is that you said, should we go online to do that? And the answer is no, you should absolutely not go online to do that. And the reason you shouldn't do that is because a lot of these companies offering direct-to-consumer microbiome tests use sequencing technologies or ways of mapping the microbiome which are not particularly robust. They used varying amounts of bioinformatics which are not standardized. And the other kind of perhaps bigger problem is that making sense of what to do with the microbiome is also quite challenging, because in many ways, we don't really know what a healthy microbiome is. Like, it's very difficult to know whether or not the microbiome that you've got today is profoundly abnormal. And I think there's nuance in it. And so my belief is that we should be measuring the microbiome, but in much the same way that you had clinical geneticists, I think you need clinical microbiome scientists that understand the nuance and can unpick it and can turn it into something that's actually useful. I also think we need to do a much, much better job of training and educating and supporting our clinical colleagues to understand it, right? And I think at the moment, many, primary care physicians that I meet feel just a bit overwhelmed by it. And when you're in clinic and your patient rocks up with, an 80-page report, you just where do you even begin? I mean, I've got a microbiome PhD and I don't know what to make of it, so God knows how some poor GP is going to make sense of it. And I fully understand their kind of exhaustion with it. And we just had there was just a big consensus statement that was published in the Lancet at the beginning of this year saying, we really should stop direct-to-consumer microbiome testing. But then I think we need to move towards having a standardized, quality assured process by which we as clinicians begin to use it. And actually you're starting to see that happen. So at Guy's and Tommy's, I think they have an NHS based 16S meta taxonomic approach for analyzing microbiomes in their ICU patients. And actually it's got a lot of use. When I use it in my clinical practice and I use it in a targeted way, it's incredibly helpful. And one of the most helpful functions actually of it is to say, actually your microbiome is normal. It's not your microbiome. Most of the time it's useful because it says, look, actually let's go and focus on the actual problem. Here is some data. The final thing that I would say is that how you use these tests is as important as kind of when you use them. So they are a snapshot. So what I say to all my patients when they measure these tests is that I say, first of all, they're a snapshot. They're a moment in time. It's not like your genome, which is very consistent. This is what was ever in your gut that day, and it will shift a little bit. So It's a snapshot, particularly if you're taking medicines. And the second thing is that sometimes these tests look at bacteria, but they might not look at viruses or yeasts or parasites or these other components. And so quite often it's a selective snapshot of what's in your gut at a moment. And thirdly, it's just looking at the fecal microbiome. So it's just looking at probably what was in your rectum or your sigmoid colon. It may not necessarily reflect what was in your terminal ileum or your small bowel, right? So you also have to be conscious that it's not describing your holistic microbiome. It's just looking at that very specific a part of it. So actually, if you're going to use them, you've really got to use them longitudinally, and you've got to use them in a very selective and targeted way. And they're very, very useful. For example, if you're going to give an antibiotic or you're going to give a drug, and you want to know what you should be coming back to and what a normal microbiome is. So I do find it quite helpful if you're going to do it when you're healthy and well, not when you're sick, because then you've got a baseline. You kind of know what is your normal gut, and then if you get sick in the future, you kind of know where you've got to come back to.
It's interesting. James, looking ahead, what sort of microbiome related preventative strategies or interventions do you think might become standard practice in primary care over the next sort of 5 to 10 years? Is there anything that you think is on the horizon?
I think it's all change at the moment, and I feel quite optimistic about the future. And I think one of the problems that we've had in microbiome science is that we haven't really had therapeutic options for that are evidence based and that a clinician and working on the front line can meaningfully use. So I think what you're going to start to see is probiotic formularies, so that they're going to come out and you're going to be able to say, okay, I've got a patient with X. Where is the evidence for particular strains or particular products, right? I think that will happen. Probiotics are evolving. So at the moment, they're regulated as foods. What you're beginning to see is actually second generation probiotics coming out, which are basically engineered to deliver very specific functions. Or these are probiotic strains that have been discovered through microbiome science. So a good example would be Akkermansia muciniphila, all right? And they are going to be regulated like medicines. So the FDA and the MHRA are going to say, no, these are not foods, they're drugs. And the way that we prescribe and give them is going to change. And they will be subjective to different regulatory pressures, so trials and the rest of it. FMT, so fecal microbiota transplant, is going to evolve. So at the moment, if you don't know what that is, it's as gross as it sounds. You basically take feces from a healthy individual and put it into someone who's got a disease or a problem. At the moment, NICE does approve that for the treatment of Clostridium difficile infection, but it's its only approved function in the UK. That, I think, is going to change. I think you're going to see it approve it for a number of other non-communicable diseases. For example, I think it will become ultimately used as an adjunct to some particular medicines like immunotherapy. I think it will become as an adjunct for things like ulcerative colitis and inflammatory bowel disease. I still firmly believe it has a role in functional gut problems like irritable bowel syndrome, but at the moment the evidence of that is a little bit. But I think what will happen is that we won't give fecal transplant the way we give it today. So what's going to happen is that actually it'll be selectively targeted in a much more precise way. And rather than giving a slurry, we will give capsulated formulations, which are like taking a tablet. And you're starting to see industry now get FDA approval and regulatory approval in Europe to be able to do that. And I think the use case for those products is going to become much wider. So rather than taking a strain of 3, 4, 5 probiotics, strains in a capsule, you're going to take many hundreds that are designed to recapitulate the ecosystem in a much more targeted way. I think you're going to see nutrition and diet become much more focused and much more targeted, and we're going to get much better at that. And don't forget, we've got lots of other products in our disposal other than probiotics. So we've got prebiotics, which are non-digestible fibers that have selected health benefits because microbes break them down. So inulin would be a good example of that, galacto-oligosaccharides, and those are going to become more targeted. You're going to see a growth in the market of postbiotics. So postbiotics are again typically foodstuffs, and these are the things that microbes make. So it's either molecules in their cell wall or molecules that they make, which you just give as the product rather than the probiotic itself. Or you might see combinations of all of them. And then the final frontier, like the really the big future, is synthetic biology. I don't think this is on the 5-year timeline. I think this is on the 20 to 30-year timeline. But I think what you will see is us genetically modifying and targeting bacteria in a very, very precise way. So this is what we're doing in our laboratory. So can you culture a bacteria or genetically modify a bacteria such that it will target a cancer? So it will grow within a cancer and deliver a drug. or can you use it to augment a therapy? So another brilliant paper that came out this week, or not this week, this month, was looking at engineering something called phage. So phage are viruses that infect bacteria, basically. Can you create phage to augment and switch on the way that immunotherapy works, for example? And lo and behold, you can, which kind of blows my mind. But anyway, you can, right? So I think the future is that actually the microbiome will be the target of the drug. It won't be your genome or your host biology. The microbiome will be the target.
That's really interesting. It feels like there's so much to be known, but already quite a lot already known, to be honest, isn't there? And it's just trying to access and utilize it in a really clinical and clinically relevant and evidence-based way, isn't it? And that is the challenge in primary care, is that we are, seen by a patient who wants a probiotic and wants to discuss that, but it's very hard to know how to direct them. So hopefully we're beginning to get towards that.
Well, I think you will get to that, and I think that will change, and I feel optimistic about that. But I'm interested in your comment around the microbiome. Like, I mean, one of the things that I find so endlessly fascinating about it is its complexity, right? Is that we just keep peeling off layers, and every layer we peel off, we find another layer of complexity. And I'll give you my favorite statistic, right? Which is that there's about 1,000 to there's about 2,000 species of bacteria that have been described in the human gut. The average person has about 500 to 1,000 species, but we think there's roughly 2,000, which is about the same number of species of trees in the Amazon rainforest, right? So it's pretty diverse. But we think there's about 150,000 species of phage. And we've got no idea what any of them are, what they do, how they regulate bacterial systems within the gut, how they influence our immune system. That's why my book is called Dark Matter, because it's this enormous genetic part of our health. Like, there's only, Charlie, about 23,000 genes that code all the proteins that make you, but you've got about 30 million microbial genes in your gut. Like, you're 1% or less human from a genetic perspective, right? And so I think it's kind of rephrasing how we think about health in its broadest possible sense, and I find that very exciting, very interesting. I appreciate if you're like, running a Friday afternoon clinic and it's 3:00 and you're knackered and you just got some kid with crew and they're like, should we have a probiotic or not? And you just want the answer, yes, I should give it or not. But at an existential scientific, level, like, I find it interesting, and I feel like that is beginning finally to translate into something which is clinically actionable, and I think it will continue to do so.
I think that's a really good place to sort of pull this to an end, that sort of worrying statistic that I'm just 1% human and 99% bacteria. So slightly worrying, but I'll take that away with me and think about how that sits tonight. But
you're a superorganism, Charlie.
There we go. Okay, I prefer that. Superorganism sounds better rather than 1% human. But it's absolutely fascinating stuff. So James, thanks so much for joining me today. It's been really interesting, kind of exploring this topic and shedding some light on what I think is going, as you say, is going to be a really interesting area over the next 10 years. So I think it's a sort of watch this space scenario. But thank you so much for joining me, James.
100% my pleasure. Thank you for having me.
Brilliant. Thank you.